Good morning. Today we'll discuss about the series RL, RC and also RLC circuits. In the last lecture, we have discussed about the basic single phase AC circuits and we have seen the basic definitions of impedance and also what is the response in a simple resistor, inductor and capacitor when they are excited with single phase AC supply. And we have also done simple problems on determining the impedance of the individual network elements. In today's class, we will see the response in RLC circuits. We will take 2 or 3 elements of R, L and C and we will see what is the response of these networks when they are excited with single phase AC supply. So I'll start with series RL circuits and then I'll move on to RC circuits and finally RLC circuits. But before going for this, why you do have to study all these things and why you should determine the impedance and response in these elements? Because you being an electronics engineer, you will be using them in all of your electronic courses and projects exclusively to control the currents. In other words, you can control the voltage also. If I mean the word control means either you can minimize or you can maximize, or let us suppose you can want to stop the current at some point of time and allow it at some other point of time. You want to block the voltage, you want to cut down the voltage or minimize the peak, or in other words, you want to filter some signals, you want to filter out some harmonics. So all these things can be done by using your simple RL, RC and RLC circuits. Depending upon your choice of R, L and C, you can choose to do all these things. Because as an electronics and communication engineer, your job is to design an electronic circuit to control all these parameters which we generally see in our electrical circuits. So one is you will be controlling the signals. So you will be developing electronic circuits which control the parameters of electric circuits. And what are the parameters which we have seen? The common parameters are V, I and F, right? So you will be trying to develop some circuits through which you can control this V, I and F. And those circuits generally do have R, L and C as basic elements. So in today's class, let's see what happens when these elements are excited by a single phase AC supply. We will discuss each of these circuits. We will try to calculate impedance and also we will try to observe the waveform of the current when it passes through your RL circuits. Okay. So I'll start with the basic series RL circuits, which is widely used in filtering also. So now if you carefully see, this is a series RL circuit. See, this is your supply. I'll assume that this is single phase AC sinusoidal supply, where this is my peak value of the signal and this is the angular frequency, which means that my input is like this. Okay, this is the value of Vm and I'll take this one as the time period. Okay, and omega is equal to 2 pi by t. If this is the thing, then it is given by the mathematical equation V of t, instantaneous value of voltage, is equal to Vs sine omega t. Okay. Now this is an R and L, combination of R and L, these are connected in series and are excited by a single phase AC source. See, consider a resistance and inductance which are connected in series and excited by a single phase AC source with the input voltage given by, this is the instantaneous voltage V of t is equal to Vm sin omega t. Now the circuit consists of two elements, right? And each of these elements, when the current tries to pass through this circuit, each of these elements, they will oppose the currents. In what way they oppose? The resistor directly opposes the flow of current, whereas inductance opposes only change in currents. And whatever the opposition is, we call it as impedance, right? So the impedance which is offered by R is given by R. We have seen it in the last class. And the impedance which is offered by inductance is given by Jx. Since it is L, see this is called as inductive reactance XL. This is called as inductive reactance XL, which is given by omega L, where omega is 2 pi by t. So, okay. Now, what is the impedance of the circuit? Now we do have two elements. Now one is R, the other one is L. Both are having, this is R and this is inductance, right? This is R, this was L. The impedance offered by it is R, whereas the impedance offered by it is JXL. Now both are in series, right? When both are in series, what we will be doing? Z is equal to Z1 plus Z. Here for the first one it is R, for the second one it is JXL. Right, so this is what I have written here. This is the total impedance of the circuit, where XL is equal to omega into L, where omega is angular. Okay, now this is a complex representation, or what we call it as a rectangular representation, right? So its polar form can be written as a magnitude and a phase angle. So how to obtain this magnitude? Magnitude is equal to mod Z is equal to square root of R square plus XL square, right? Where XL is omega L. And the angle, it can be obtained from tan inverse of imaginary component by real component. Tan inverse XL by R. Okay. So now, so for the impedance we have obtained, Z is equal to R plus Jx. Or I can write it as R plus J omega L. And what is the voltage? Vm sin omega t. This is the mathematical representation. I can write it in polar form. This is also can be written in polar form as mod Z triangle of theta, where Z is equal to square root of R square plus XL square, and theta is equal to tan inverse of omega L by R. So when I want to determine the current in this series RLC circuit, what I'll be doing here, I is equal to V by Z, isn't it? I is equal to V by Z. Where this is V, this is Z. So when I use the polar form representation, this is the polar form representation. When I represent my current in this format, see what is the actual magnitude now? It is Vm by Z. And the angles they get subtracted, right? Angle minus pi, right? So if I expand this Z, what is mod Z? Magnitude of Z, we have seen in the last slide, square root of R square plus omega L whole square. So this is the current which is flowing in the circuit. Understood? So I'll write it here, I is equal to Vm by, I'm considering only magnitude, square root of R square plus omega L whole square. It's an angle of minus theta or phi. If you want to represent it as phi, it is phi. Okay. So in series RL circuits, so we have already done the impedance calculation and also the current calculation. Now comes the power factor. As already I said, power factor of the circuit is given by cosine of the phase difference between voltage and current signals, isn't it? So in this case, what is the phase angle of the voltage? V was given as Vm sin Vmz, right? Whereas I was given by Vm by square root of R square plus Z square into, sorry, x omega L whole square, right? This is tan inverse of xl by r. This is what we call it as phi, right? It was minus phi. I'll show you. Yeah. This was minus phi, right? So, what is the voltage? Phase angle is 0, current phase angle is minus phi. So, what is the difference between these two, 0 and minus of minus phi? I'll get phi. So, power factor in this case is cos of this phi, which is written as cos of tan inverse of omega L by R. In this case, in RL circuit only. This formula is valid only in RL circuit, because in this circuit, phi is tan inverse omega L by R. This is a generalized formula. In this case, phi is tan inverse of omega L by R. Right. Now, if I expand this one, now if you see tan inverse of omega L by R, cos of tan inverse of omega L by R, I'll get R by square root of, this is my representation, or I can write it as R by Z, magnitude of Z. Try to remember, this is one more generalized formula. Power factor is cos phi, or you can write it as R by Z, whatever the total impedance magnitude. Don't use complex number here. Okay. So this is one more representation of power factor. I hope you do remember this formula. Power factor is equal to cos phi, that is equal to R by magnitude of Z. Now let us see the response. Now this is a sample response of an RL circuit. If you carefully see, the red indicates a voltage signal, whereas the current indicates the blue indicates a current signal. If you carefully see, the red signal is starting at 0, but whereas the current signal is starting at somewhere at here. See, this is 180 degrees, this is 360, this is 270 degrees, this is 90. Now if you carefully see, the current is starting somewhere between 0 to 90, and it is lagging the current by some angle, right? So, and that angle, cos of that angle is now being considered as a power factor. Okay. Now the difference of angle between voltage signal and current signal, and the cos of it is called as a power factor. So power factor in this case, worst case it is 0, and the worst case it is 90, right? So it will be 1, that will be 0. So for a RL circuit, the power factor will be varying between 0 and 1. Because for a pure resistor, it would be 1. For a pure inductor, it would be 0. See, power factor for a pure R circuit, it is 1. For a pure inductor, it will be 0. Now for a RL combination, it will be between 0 to 1. Now what is it? It is considered as a lagging if it is inductive in nature. Try to remember this one. It is considered as lagging because current is lagging. Because it is always said with reference to the current. So since current is lagging, power factor is considered as between 0 to 1, value will be lagging. Okay. And see the phasor representations. Now I will say the phasor representations. Now Vs is equal to Vr plus Vl, right? This is one standard thing. So normally if I take currents as a reference phasor, Vr will be in the same direction as the currents, whereas Vl, it will be in 90 degrees, voltage will be leading currents in an RL circuit, right? So this is Vl, and the combination of these two is your supply voltage. This is the phasor diagram, right? Current, with reference to the current, I am drawing this. First of all Vr, and then Vl, but with an angle, and Vl is 90 degrees, right? So if I join these two, I will be getting Vs. This is called as a phasor representation of the voltages. Understood? Now, if I remove, if I can write this one, see, this is a R, this is XL, and this is Z. Okay, this is called as an impedance triangle. We call it as impedance triangle. Try to remember these things. Draw the impedance triangle for a series RL circuits. Okay, represent the phasor quantities. These are two of the figures which are to be drawn in case of series RL circuits. Okay, and RL circuits are exclusively used in tuning, frequency tuning in electronic circuits. You'll come to know when I teach you analog electronics in the next semester. Okay, so I'll end this video here, and in the next video we'll discuss about series RC circuits. Okay.